So thank you for coming to the seminar. Luca Carloni is gonna give a talk. So I've been following him for a while since he was in Berkeley. So he was working on elastic systems and some other things. And now he's a professor at Columbia. He's working with an open source hardware infrastructure framework, and he's been having several tutorials on the conference. So thank you for coming. Very good to have you.
Thank you for the invitation. So yes, I've been at Columbia now since 2004. And what I will present to you today, which is ESP, an open source platform for heterogeneous computing, is really the result of the research that my group at Columbia has been doing for almost 8 years. So of course, I'm not going to present all, all the things we have done in 8 years, but ESP is this project that we made available in open source in 2019. And really quite a bit of the research we are doing at Columbia is based on ESP, contributes to ESP or leverages ESP. And so you'll see how after a motivation part, an introductory part of my talk, I will discuss the key aspects of ESP. And then towards the end of the talk, if time permits, I will show you how we actually use ESP at Columbia to do research, to do other projects, and also for teaching. And hopefully you can find this interesting and inspiring. So first, a little bit of motivation. Actually, our research for the last 8 to 10 years has been motivated by this consideration that we are going more and more towards an age of heterogeneous computing in terms of information technology industry in general and semiconductor industry in particular. The system on chip has become the dominant architecture, the dominant computer architecture across a variety of systems. So an SoC, there is a representation, is a computer architecture that really combines a variety of different components that have different natures. In this sense, is a heterogeneous architecture. So you have different CPUs, GPUs, an increasing mix of fixed function hardware accelerators, and then various memory modules, some reconfigurable engines, peripherals, sensors, and so forth. And in my opinion, we will continue to observe a migration towards heterogeneous SoC architecture across pretty much all computing domains, from IoT devices and low-power embedded systems to smartphones, high-performance embedded systems, industry like automotive, electronics, all the way to data centers and supercomputers. And also I have a prediction that I've been making now for some time, which if you look ahead, like, maybe 8, 10 years from now, in any given year, like in the year 2030, the set of heterogeneous system on chip in production in that year will be itself heterogeneous. In other words, I don't think that there will be a single SoC architecture that will dominate all the markets, but there will be a variety of different SoCs for different domains, for different application-specific domain across different markets. And this, of course, offers a lot of opportunities for innovations, for research, for entrepreneurship, and so forth. Now, we don't go into all the details why there is this migration towards heterogeneous architecture. It will be sufficient to say that for trends, which are both technology trends and economic trends, there is a continuous quest for higher energy efficient performance. And this is really what the combination of different components, in particular fixed function accelerators, combined with general purpose processors, or sometimes application specific processor, is this yield this architecture that give you really a major gain in terms of both performance and energy savings, power savings. However, heterogeneity makes the design process, the verification process, and also the programming more difficult. This is because at design time, you have naturally diminished regularity, the more heterogeneous is your system. This is true at the level of computer architecture, at the level of the logic structure of your system on chip, for instance, and certainly also at the level of physical design or chip layout. At runtime, you have to manage more complex interaction between hardware and software. You have to manage resources across processors and accelerators, so across components that have a different nature. And there are some shared resources like, you know, access to external memory, the power envelope that you can dissipate at any given time, that, you know, are shared, but now you have to be managed with, across components which are different. And this makes the whole process more difficult. So with each system on chip generation, it has been noted that the addition of new capabilities is increasingly limited by engineering efforts and team sizes. So there is a problem of design productivity, if you will. And in my opinion, the biggest challenges are today and will increasingly be found in the complexity of system integration. So this problem of integrating components that have a different nature. Now, this seminar series is the open source hardware seminar series at Santa Cruz. So probably you don't need to hear this from me, but you may have noticed that over the last few years, this movement of open source hardware has been growing, has been gaining momentum. And I really see it as an opportunity to re-energize the innovation in the semiconductor industry and also in the EDA, electronic design automation industry, the industry that provides the tools to help design and program semiconductor and in general computer systems. And so you have a variety of contribution from both academia, from industry, and from different organizations. You have now this multi-institutional organization that have been created to manage in some of these open source hardware components. And you have quite a bit of support from government programs in terms of funding to promote open source hardware. So I think it's a great opportunity, particularly for research also in academia, and to realize a more interesting system. However, to a certain extent, we and our group have identified some sort of a challenge that remains open. We have also observed that most open source hardware projects are focused on the development of individual components like a processor core or a particular accelerator, very important for some particular application. And this leaves open a critical challenge, which we can try to state as follows. How can we realize a complete system on chip for a given target application domain by reusing efficiently and by combining efficiently a variety of independently developed, heterogeneous, open source hardware components, especially if these components are designed by separate organizations for separate purposes. And our work, our research focus particularly on this critical challenge. We are not the only one, but this is what motivates our research. And we have a concept that we have been working and we have been developing for quite some time, which we think can provide very efficient methodology, the basis for building a methodology and architecture. And this is the concept of platform. So what you have that innovation in system on chip architecture and in the design methodology, the EDA, the electronic design automation methodology, is needed to promote the reuse and the collaboration for building this system. So open source hardware, of course, is the general movement. People develop components and make them available in public domain. And so it is important to facilitate the reuse of this component to create collaboration, if you will, over space and time across different teams to allow the continuous innovation, both in the architecture and the methodologies. And in our opinion, it's important to a certain extent to try to develop the architecture and the methodologies together. So really the concept of platform is the combination of an architecture and a methodology. Now, an SoC architecture enables design reuse when it simplifies the integration of many components that are independently developed. An SoC methodology enables design collaboration when it allows designers to choose the preferred specification languages and design flows, and with the design flows, the tools for the various components. And different components may be more, may have to be designed and developed using different languages and different design flows. So an effective combination of architecture and methodology is a platform that maximizes the potential of open source hardware by scaling up the number of components that can be integrated in the SoC, and by enhancing the productivity of the designers who develop the components and use the components to build subsystems or complete systems. So if this is kind of clear, then ESP is an example of a platform, is an open source research platform. It has been open source, as I said, since 2019, focuses particularly on SoC design, although I would say in general is an example of a platform for heterogeneous computing, potentially also beyond SoC. It combines an architecture and a methodology. The architecture is a scalable architecture because it allows the rapid design and FPGA-based prototyping of fairly complex SoC by combining newly designed components with open source hardware from the public domain. The flexible methodology guides designers through the development of new components, in particular specialized hardware accelerators, and the integration of this component into the heterogeneous architecture. In doing so, the methodology supports a variety of specification languages and really embraces a mix of open source and commercial CAD tools. So it does not dictate one particular specification language for instance, accelerator or for a hardware component, nor a particular design flow. It tries to, as much as possible, be flexible and accommodate different design flow and different languages. And in fact, this is where also there is the opportunity to contribute to ESP, as it is, as there is the opportunity to contribute to architecture by developing components. So as I mentioned before, it's the result of 8 years of research in the system level design group at Columbia University. This is the web page of ESP. And I'll invite you also to visit it at the end of the talk. There are a variety of resources that we have made available. We recently made a new release, and we continue to try to expand the resources that we have on this website in terms also of documentation and tutorials of various formats. I'll say a little bit more about that towards the end. So if there are no questions at this point, this is kind of the introduction and motivation of our research. Then from now on, I'll structure the talk with 3 main segments. So first, I will give you an overview of the ESP architecture. Then I will illustrate the ESP methodology and certain aspects which I consider maybe more interesting and more critical of the methodology at this time. And then I'll give you some examples on how we use ESP also to do other research projects, sometimes contributing to ESP, sometimes just leveraging ESP to make research contributions that are somewhat independent from ESP, but they use ESP as a way to make experiments and evaluate our research. And also, I'll mention how we use ESP also for teaching at Columbia, and how we are trying to develop resources that allow other groups and other professors to use ESP for teaching if there is interest for that. So I'll stop 1 second in case there are any questions.
No, I think you are preaching the converted with the open source.
Okay, very good.
So
that's fine. So let's go. So let's start with the architecture. So the ESP architecture, as I said, is like one of the 2 key components. We have the architecture and the methodology, and they are developed together. So as you can see from this slide and from the next few slides, we made some important assumptions, and we made them after carefully evaluating how to find what we think is the right balance between regularity and specialization, the specialization coming from the heterogeneity of the component. And so we came up with this tile-based architecture. So here you have an example of a particular instance of an SoC built with an ESP architecture. It's a tile structure, 4x4, so 16 tiles. And as you can see, the color coding shows the 3 main types of tiles. You can have also other types of tiles, but this, you see, you have the reds, which are the processor tiles, the green, which are the accelerator tiles, and the blue, which are the memory tiles or IO tiles. Everything is connected to a multi-plane network on chip. My group has done quite a bit of research on network on chip, and for ESP, we settled with a 2D mesh topology for the network on chip. Multiplane means that there are multiple physical planes that can be configured. In fact, the number of these planes may vary. It's one of the many configurable aspects of ESP, and where we again try to find a compromise between adding some degree of configurability while also having a certain degree of regularity in the architecture. The regularity is important because it allows you to make certain assumptions when you develop the components, and also when you develop the methodology, the design flows that really are the embodiment of the methodology. Overall, the architecture implements a system which is distributed. The network on chip, of course, creates a communication medium and adds a certain degree of latency in the communication. Is scalable. And I'll show you example later on, but you can imagine that to a certain extent, you can choose the number of tiles, and a lot of the properties of ESP remain valid, regardless of whether you have a 3x3, a 4x4, a 6x6, a 6x5. Doesn't have to be square.
So okay.
Please.
Sorry.
No, please.
There is an echo. So I have a question about the NOC. So yes. Is it tiling? Is it AXE, or is it your own protocol? What do you?
The NOC is our own NOC developed by us. Is a 2D mesh packet switch NOC, and as will be clearer in a few slides, there is a key concept in ESP, which I'll explain in a second, which is the concept of socket, which for now, just let me tell you, wraps around each tile, and that is where there is the interface with the NOC, and that is where we provide support for communication with components that speak standards like AXE or AMBA or some other standard. But the NOC per se right now is our own NOC. So it has in terms of flow control, in terms of routing as our protocols. It is also true that it's conceivable to replace the NOC with a different NOC or with a different communication medium because it, like many things in ESP, the modularity is also a modularity of the design. So the design of the NOC is very decoupled from the design of the tiles.
Now, and then one question to clarify on the multi-plane. The multi-plane is, you have physical links. You have multiple physical links, or more like virtual channels?
No, okay. You could also add on top of multi-plane virtual channel, and I can point you to a study we did in the literature, even before ESP, on the pros and cons of having just only multi-plane or also only virtual channel, because as you certainly know, they are multi-plane and virtual channels, multiple physical plane and virtual channel to a certain extent can be seen as alternative solutions for certain issues. Like for instance, if you want to support protocols avoiding the problem of protocol deadlocks, and not just because you want to increase bandwidth. If you look now to the ESP distribution, we don't have virtual channels. We have multiple physical planes, and each physical plane has a parallelism, if you will, a bit width, which may be configured. So you could have a plane which is 64-bit and another one which is 32 or 16 bits or even 8 bits. And this is because different planes typically are dedicated to different type of communication. However, this is configurable and modular.
Okay.
And of course, it's heterogeneous because you have this mix of components. So the idea of the trade-off, the balance, is that for a particular application, you may want to develop a particular SoC, and you have to decide how many tiles you want, which kind of mix of tiles you want, how many processors, how many accelerators, how many memory. And I'll give you an example throughout the talk. So briefly, let me introduce each of the key components. So you have the processor tiles. My group doesn't do particular research on the architecture of the processor. We leverage open source hardware quite a bit. So right now in ESP, you have the choice of two main types of processors. And recently we had a third. The two main types of processor are RISC-V Ariane 64-bit developed at Zurich. The other one is Spark V8 Leon 3, 32-bit, which is developed by Cobham Geisler. And these two processors are, of course, different ISAs, but they both are able to boot Linux. They both come with a private level 1 cache, and the ESP tile augments them with what is a unified private level 2 cache, which you can configure in size. So what you see in the corner there, inside the tile of the processor, we instance the open source hardware component, and then inside the tile we add this level 2 cache. And notice that this integration is to the distributed ESP system is transparent. What do I mean with that is that there is no ESP specific software patches that need to be run in order to boot Linux. So we integrate them, we allow the user to decide the size of the level 2 cache, and we have, together with the level 2 private cache, we have one particular protocol for coherency in case you have multiple processors and you want to have a coherent system. So we have a MASI protocol distributed. I'll tell you a little bit more about that later on. And then we have a certain, inside this gray part of the tile, you see, probably you notice that each of the colored tile, blue, red, and green, there is this gray wrapper around them. That is where the socket is. And in the case of a processor, the socket also implements these services related to communicate with the NOC with respect to coherency and interrupt request. So for example, typically to support MASI protocol in a proper way, a NOC needs to have either 3 physical planes or at least the ability to support multiple 3 virtual channels. And in our case, we have 3 different planes of the NOC that guarantees proper support for coherence. Then you have the memory tile. So now the memory tile typically is where you have the SoC system that speaks with external DRAM. So you have in general the memory controller. Now, as I said at the beginning, ESP has a quick path to offers a quick path for FPGA prototyping of SoCs. And so what that means is that you can, from the FPGA instance, the memory controller and access directly to the RAM. And then inside the memory tiles, you instance the memory controller and you have all sorts of circuitry already designed. You just have to configure to support various types of communication with external memory. So coherent access to memory, direct memory access, DMA, which is very important for accelerators, and so forth. Of course, if you have a system with more than one processor, typically you may have that you want to have a coherent system. And I said we have this MASI protocol. And so you may also have multiple memory tiles. Like in this drawing, you see that at the 2 corners, I guess the northwest and the southeast corner, you have 2 different memory tiles. So then what you have is that ESP gives you automatic capabilities to split the addressable memory space and have half of the memory being addressed with one memory tile and the other half with the other memory tile. This also automatically split the last level cache, LLC, as well as the directory. Everything is distributed, and let's say the support for coherency is already given. So is a service, again, that designers can leverage if they want to develop a system that requires to have multiple processors and multiple memory tiles. Then you have the accelerator tiles, which is the third main type of tiles, and often is where a lot of the, if you will, innovation in terms of the target application for an SoC is, because of course is where you have that in many SoC systems, for particular for high performance embedded systems, you have that there are key computational kernel, key algorithms that it makes sense to develop in hardware as opposed to run them in software on a processor. And so these accelerators give you, compared to a software execution, order of magnitude gains in terms of energy efficiency and performance. And a lot of our research is on designing an accelerator and developing design flow for simplifying the design space exploration process or when a designer develops an accelerator. So, also the accelerator tile, like the other, as you see, is encapsulated into this gray block where there are various functional services, like in this case, an accelerator can have different coherency models. I'll tell you more about that a little bit later, but we support communication that is non-coherent or coherent just with the last level cache or fully coherent with the processor. And we have done some research on this showing that it's not necessarily the case that one model is always the best for accelerator, depends on a lot of considerations. And then we have certain capabilities to configure the accelerator. Accelerators really, in general, these accelerators are not programmables in the sense that don't execute software, but they are somewhat configurable and to a certain extent reconfigurable at part time when they get involved. And of course, distributed interrupt and so forth. So a lot of the innovation is in the different accelerators, but even here you see that there is a decoupling between the design of the accelerator and the interfacing of the accelerator with the rest of the system. So finally, we arrive at this concept that I've mentioned already a couple of times, and is a critical concept on the architecture side of ESP, which is the concept of socket. Sometimes also we refer to it as the wrapper or a shell. And the socket, here I show it for the example of the accelerator, although some of the concepts that I'm mentioning here apply also for the memory tile and the processor tile. So basically, let's start with the figure on the left, which is an accelerator developed, let's say, from scratch by a designer using one of the various design flows that I'll mention later when I'll talk about the methodology, which are supported by ESP. So you can develop an accelerator with different design flows, and you can rely on the fact that this accelerator can be encapsulated automatically, thanks to our methodology, with a socket, which is configurable and provides the interface to the network on chip. And again, here, this is an example where you see that the network on chip at the bottom, you see those numbers, 1 to 6. Those are the example of a network on chip with 6 planes, which right now is often a number that we find useful for the type of system we are developing at this time, of which 3 planes usually support the communication between processor and memory, but also between an accelerator and memory if the accelerator has been instanced also with a private cache and participates to the coherency with the memory. That doesn't have to be the case. It's something that is configurable. So you can also have an accelerator that doesn't have this external private cache and just communicates through either non-coherent DMA or coherent DMA planes with the last level cache. You have the equivalent of a TLB, which allows you to access, of course, properly the physical memory, where the data are, the data that have been put there by software running on the processor, while the accelerator has been designed independently from that. And so this implements for you the translation. Then you have configuration register, as I mentioned before. You have the interrupt, which is used to interact, of course, with the processor when the accelerator is done and has finished computing. Later on, when I'll talk about the methodology, I'll give you an example of a typical flow of computation of an accelerator. What you see here is an example of an accelerator socket for the left-hand side with all the main features. On the right-hand side, you see the example of a different socket. You see there is this asterisk, and this socket is for a socket that, for instance, we have for a third-party accelerator that has already been designed and is not designed with the ESP methodology. So, for example, you may be familiar that there is this NVDLA, an accelerator for deep learning made available as open source in public domain by NVIDIA Research, and is an accelerator which is very similar to the principle of the computation that it does to the type of accelerator that you want to develop with ESP. So it's a coarse-grained, loosely coupled accelerator. Coarse-grained meaning that executes complex tasks. Loosely coupled means that it executes these tasks independently from the processor. The processor allocates the data and invokes the accelerators and lets the accelerator process those data while the processor does something else. And when we integrated the NVDLA, what we noticed is that some of the services that we typically put into the socket were already implemented inside this accelerator. This, after all, was an accelerator completely designed. And so it was not necessary to replicate them. And also, this answered a little bit the question that Jose asked. In this particular case, this particular accelerator speaks the AXI4 bus and AP bus for configuration, the AXI4 for the communication of data. And so in this case, the socket on one end doesn't need all the typical features that the general ESP accelerator socket has. And so those can be in a very modular way remove, not instance, when you synthesize and integrate this accelerator. On the other hand, we have created interfaces such that the network on chip can communicate effectively with this particular accelerator that speaks these standard protocols. And of course, any other accelerator that speaks this same protocol, we can leverage this effort. So hopefully this explains the concept of the socket, which is the hardware software. If you will, we also have a notion of a software socket, because of course the accelerator provides an effective implementation for an algorithm, for a computation, like a neural network or some computer vision algorithm or an FFT or something like that, some coarse-grained task. But the accelerator has to be invoked from software, from applications. And so we develop an API, an application programming interface, that allows us to really generate the device driver, a unit test application in an automatic way, simplifying a lot the first task of evaluating an accelerator and invoking it from software. So you have the typical application software, and this can leverage an ESP library which interacts with the ESP accelerator drivers. And this is all built on top of Linux, like a Linux module. So it's very modular. And the API is simple. There is a way to allocate data in software from the application into a buffer, such that then you can, instead of invoking a function, a software function, for certain kernel, like here for the 3 kernels in particular, you may want to decide to invoke the accelerator, pass the configuration, which has all the information about where the data are that have to be read by the accelerator and where the data should be written by the accelerator in main memory. And then the computation occurs through an invocation of this API call, which really translates into a system call into the device driver and the invocation of the hardware. And so we have found that this is simple, is effective, the overhead is minimal for coarse-grained tasks, which is really what we are targeting with this type of accelerator that we are developing. And it simplifies a lot, because typically when we develop a new accelerator, or even in class, when students design a new accelerator, typically they first have an application, maybe a testing application, starting from the one that we generate automatically. And in this application, they can first have an implementation of the function that the accelerator does done in software, and then they can replace that with an invocation in hardware, compare the two, validate the correctness, and then evaluate the performance gain, because of course, doing the execution with an accelerator is supposed to provide speed up and energy gains. Okay, so this with respect to the API, the programming. As I said, we have a variety of services that are implemented into this socket and supported by the network on chip. Some services are common across different tiles. Others are specific of certain tiles. So here you have many of them. For instance, accelerator tiles, you have already DMA implemented for you. If you want, you can have different degrees of coherency models available for the accelerator. You may have point-to-point communication between accelerators instead of interacting through main memory. And you can have dynamic voltage frequency scaling if you want each tile to be able to change, to have the frequency and the voltage change dynamically during the execution. And so the controller we have developed and is another example of a service that you have inside the socket, and many others. And so again, the idea is that in this way, for instance, an accelerator designer does not have to reinvent the wheel, but can rely on all these pre-designed and pre-validated services and focus instead on developing a very interesting accelerator for a very interesting application, for a very interesting SoC. So this is a little bit the idea of the services. So this ends the part on the architecture. I stop 1 second in case there are any questions. Okay, so if there are no questions, let's move into the methodology, which is the companion of the architecture. And of course, has been developed relying on some of the assumptions of the architecture. So first of all, we have a fairly ambitious vision in which at some point, application-specific domain experts can design heterogeneous system, at least SoC prototypes with FPGAs. And we are not there yet, but we are making progress, I think, in that direction. And the ESP vision is kind of captured by this picture. So what you see on the left-hand side is the variety of specification languages that can be used particularly to develop accelerator, of course, also to develop other components, if you will. But if we focus on the idea of enabling designers to develop quickly a new system on chip, reusing processor, memories, network on chip, and as well as all the services, and really focusing on innovating with respect to the development of software and the development of hardware that this software invokes, meaning the development of accelerators. Here, what you see is the different languages that people can use to specify hardware, in particular accelerators in ESP. So each of these languages comes with a flow. So for instance, you can use RTL design, Verilog, VHDL, or Chisel. You can work at a higher level of abstraction, which is what we typically recommend in many cases, particularly for accelerator, and use a system C or C++. And of course, if you use RTL design, then you have the classic RTL design flow. If you start from system C or C++, then you can use some of the high-level synthesis tools, commercial high-level synthesis tools that are made available by EDA companies, and that allow you to synthesize the hardware for this accelerator, and then you can instance and rely on a lot of automation on the ESP methodology to create a socket around this hardware and integrate it into the system. And then on top, please.
Sorry, I have a question. So because you have a tile system, the
Yes.
intuition will tell you, oh, you synthesize each one of the tiles, and then you can load them on the FPGA. But the FPGAs tend to be a little bit difficult to use macros. Many times they give you problems. So do you have that enabled? So, or do you have to?
I'm sorry, it's difficult in particular to use what?
Macros. It would be like a macro on the FPGA so that you pre-place and route on the FPGA. Or do you have to place and route everything when you upload a new design? Or do you understand what I mean?
Okay, no, that's a good question. That's a good question. As of now, every time we do a design, we rely on the physical design flow for FPGA, as you say, the place and route. So we place and route the whole thing. But we are working, it's not ready for prime time yet, but we are working on partial reconfiguration. So to avoid having to redesign the whole thing. That is not a feature that is available yet, but is on our path. So right now, yes. So I guess what we have is that, as you can see here, we have this library, this software library and the hardware library. And then if I go ahead, and then I'll step back and go to the other point, we have a capability, we have a graphical user interface that simplifies the integration of the components with the NOC and the socket, and then really can, to a certain extent, push button capability to do FPGA prototyping. But yes, we don't develop CAD tools for FPGA. We rely on commercial offering for that. So
you generate Verilog at the end of the day, and then that is you upload, or you in the C case you use the Xilinx. I guess you have
we right now, although it's not limited to that conceptually, but right now we mostly use the Xilinx flow, and certainly it is the case. Well, if you work at the RTL, Verilog, VHDL, doesn't matter, of course. If you work at the level of C++ System C, then you go through this high-level synthesis tool that typically produces Verilog, synthesizable Verilog, and so that goes through and gets synthesized on the FPGA. If you work at the higher, an even higher level of abstraction, we only have one example of application domain design flow. I'll mention it again at the end of the talk, is this flow where for embedded machine learning, so for a particular subset of machine learning, very low power, I guess, so it's fairly small deep learning network that you can specify using Keras, TensorFlow, and PyTorch. And here we leverage another open source project, which we contribute, but it's not our project. It's called HLS4ML, a very interesting project. And this project takes this specification with this common framework for machine learning and produces synthesizable C, which then you can go and, in particular, for example, give it as an input to the Vivado high-level synthesis tool and produce the Verilog that then you put on the FPGA. And of course, what we put around that is all the mechanisms to add the services and the sockets so that you can integrate the accelerator for machine learning with the rest of the system. Okay?
Yeah, sounds good.
Okay. So then let me tell you a little bit more. So this is just to say that the color coding here, you see that the top right corner, tells you a little bit about the degree of automation that you have for the design of a particular accelerator, what is called the accelerator flow. Of course, there are multiple accelerator flow depending on the particular specification language and the particular synthesis tools, but certain aspects of the flow are common across them, and the principles are common across them. So you can interactively, if your accelerator falls into a category of coarse grain accelerator working in streaming on data, where really during an invocation of the accelerator executing a complex task, the accelerator goes through a sequence of reading from main memory, computing locally, and writing back into the memory. I'll tell you more about that in a second. We can already, through an interactive flow, generate some sort of a skeleton accelerator where you have a basic, the basic mechanisms, particularly this applies to the flows for high-level synthesis, and then you can specialize the internal part, the computation part, and specialize the accelerator. Of course, if you go for the machine learning application for the domain specific, that is also automated. But typically, if you do it as accelerator, which is not based on the flow that I mentioned for embedded machine learning, then this is where the designer designs the accelerator, design the computation part. But we gave a template, a skeleton that simplifies a lot the process to get started. And then we also automatically generate a way of testing the accelerator and the device driver, which again, to a certain extent has to be configured because different accelerators have different configurable registers, but the large majority of the code of a device driver remains the same for different accelerators. And then, of course, you have different accelerators you put in the library, and then you have this graphical user interface where you have the SoC flow, which generates the sockets, allows you to configure the RISC-V SoC, for instance, if you do RISC-V, assuming the RISC-V is the processor, and you decide how many tiles. You can immediately go through a compilation for bare metal and simulate the system. And then, of course, you can also configure the runtime, compile Linux, and deploy the prototype and run applications on top of Linux. And to a large extent, these tasks are either interactive or automated. Certain aspects, there is a little bit of manual effort. I would say the biggest manual effort is the actual design of the accelerator that I'll mention, that I'll focus now in a second. And this is, if we go into the accelerator flow, particularly if you use design flows that start a higher level of abstraction than RTL, which we advocate for many accelerators. So what you do is that you develop initially this programmer view, where, for instance, let me make the example of System C and high-level synthesis. So you do a synthesizable System C specification of your accelerator, and then and you work at that plane, the top plane in this figure, and then using high-level synthesis tool and the capabilities of high-level synthesis tools for each specification, you can automatically synthesize multiple implementations, RTL implementations, for instance, in Verilog. So this is high-level synthesis does it for you. And high-level synthesis provides, as you may know, knobs that allow you to change the microarchitecture of the implementation. And so that is what is called design space exploration. Typically, you trade off cost, a cost metric, which is a combination of area and power, versus performance. For instance, you want to minimize latency. And to a certain extent, you can do this using high-level synthesis. At some point, you may need to change your code. So there is a design effort. But the design effort that we advocate happens at a level higher than RTL, happens in System C. And so you focus more on a level which is closer to software, if you will. Instead of being concerned about deciding what each signal does at each clock cycle, you work more on the level of data type, data structure, and operations on this data structure. And you focus more onto issues like how much pipelining, how much parallelism, and so forth. And high-level synthesis, of course, supports you that. So this is an example of an accelerator that we developed a few years ago, in fact. And there is citations there. I still use it because in some sense it is paradigmatic. This is for a computer vision application, wide area motion imagery. So you take the input from a sequence of frames and you detect the extract masks of meaningfully changed pixel. In this case, you see some fish swimming in a pond, and they get detected because they are the main things that moves there. And so when we developed this application, which you see the block diagram on the right-hand side, it has some classic computer vision algorithm. My students didn't have particular experience on computer vision. So we started from a specification given in C, and you see the lines of code for the various components on the bottom right corner, about 1,000 lines of C code, not developed by us. What we developed is the system C version, system-sizable system C, because this C was not synthesizable. This C was for running or being compiled and run on a processor as software. System C instead was synthesizable hardware. And you can see also, which is fairly characteristic, System C is a little bit of a cumbersome language in certain regards. So you can see that you need more lines of System C, but you are designing hardware. And so you're making some important microarchitectural decisions. In fact, you make decisions that using the high-level synthesis knobs can lead to many different microarchitectures. And then the RTL, which is even more lines of code, is automatically generated. And so it's not surprised that it's more lines of code, and it's really not code that you want to look at. So if digging a little bit more on this concept, this is another example, is another kernel. This is a typical simple example of what you can do when you work with C or System C. So here you have a function that has nested loops, and inside the second nested loop, you have a certain computation of a function with a certain degree of complexity and then accumulation. And so what you can do, you can use high-level synthesis tools to decide to which extent, how you want to implement these two loops, which operate, of course, on arrays. And this is often the case also, not just for signal processing, but for computer vision. And so you can, as you may know, high-level synthesis tools allow you to say, okay, let's break the computation across multiple clock cycles. And this may take more time because, of course, multiple clock cycle of one iteration, and then you have many iterations, but in general requires less power and less area because you reuse resources across multiple clock cycles. Or you can do that, but or alternatively, you can start unrolling and do a little bit of spatial parallelism. And to the extent that this is possible with based on the dependency, the causal dependency between the different iterations of the loop, you can instance more hardware in parallel and start gaining in terms of performance, reducing the latency, as you can see on the x-axis, that it requires to do a computation of this function, and in exchange dissipate more power or occupy more area. And you can also do pipelining, which means that you have multiple, the execution of multiple instances of iterations of these loops, one on top of the other. And this typically requires, again, to spend more resources in power and area. So these are all things you can do. And each of those points that you see there represent an RTL implementation automatically generated from the specification given in System C or in C. So now here is where I do a quick parenthesis. Some of you may know that when I was doing my research for my doctorate, I developed this concept of latency sensitive design, which was an idea to, at the time, there was this problem that you had this was mid-90s, that wire communication on the chip, point-to-point wires, started having a delay, a latency that was not negligible with respect to the computation within the components. And so I developed an entire theory that allows us to say, okay, if you have various components, which I call core already in the 90s, and as long as these cores can be stalled, meaning that they can be clock gated, you can automatically, with very little information on the core, you just need the information on the I/O, you can automatically generate an interface we call a shell, which is made of these bypassable queues and the implementation of a protocol, which allows you to tag each data in a stream of data on whether it is present or not present, valid or not valid, and allows you to support also back pressure. And if you do that, the result is that the combination of the core that does the interesting functionality and the shell that implements these services of queues allows you to then take long wires and pipeline them with relay station, which are fancy versions of flip-flop that speak this communication protocol. So this was before network on chip, but the key concept here is that by creating automatically these shells with CAD tools, you could then automatically pipeline the wires, change the latency without having to change the design of the core. That's the key. The only thing you need to be able to do is to stall the core by doing clock gating, which is pervasive nowadays in hardware design for blocks of a certain size. And so this, in some sense, anticipates the separation of the computation from the communication that you have whenever you develop accelerators with high-level languages for high-level synthesis, like System C or C. the companies that provide you these high-level synthesis tools also come with libraries to implement channels which are very much elastic or latency sensitive. So this concept of separating the core functionality of the computation from the interface of the communication is key. Why is key? Because when you design an accelerator using System C, and this is an example, of course I have to go fast here, but hopefully you get the idea. You have, in this case, that the accelerator operates on certain data structure, which are highlighted there in blue and green. This is for a particular local memory. The private local memory, which is the memory accessible only to the accelerator, is a key part of the microarchitecture of the accelerator. As you may know, most of these coarse-grained accelerators are mostly memory, mostly SRAMs or VRAMs. And then you have processes in System C that translate, of course, to hardware when you synthesize, to do input or read, output or write, and computation. And so you see those blocks, input, compute, and output, interacting with the private local memory. And this brings the data in from main memory into the private local memory, where they get access by the computation processes. And then when the computation is completed for a certain set of data, they get written back. And of course, you want to pipeline computation and communication. And of course, here is where you see DMA controller. The DMA controller is in the socket, so it's decoupled from the design of the accelerator. Everything that you see inside there into the orange part is the design of the accelerator, for which you have the code on the left-hand side. And so what you have is that really the design space exploration, the decision of the microarchitecture is to decide how much parallelism, how much pipelining you want to have in the computation, which kind of private local memory to build. In this case, you have a circular buffer and a ping-pong buffer, the first shared by the two processes, input and computation, the other one shared by computation and output. And of course, different accelerators are different private local memories because depend on their characteristics. And this is really the art of accelerator design. But the concepts are common. You want to have these private local memory, which are multi-bank, multi-ported, so that you can support quite a bit of parallelism in the computation locally, and you can support pipelining of computation and communication. Once you have that, then if you use high-level synthesis, if you now understand that this is the abstraction, you have the input that interacts with main memory, brings the data into this particular local array, which is accessed by the computation that produce the two arrays for this particular algorithm that then get written back into main memory. And you have, of course, a little bit of unshaking. But all this is latency sensitive. Is latency sensitive inside and is latency sensitive outside in the communication to the network on chip. Why is this important? Because when you go and explore with high-level synthesis, the microarchitecture of the computation, the input process, the output process, the main memory, you may automatically generate many different microarchitecture, like the ones are shown here for the different parts of this computation. And this you generate automatically, but you have a guarantee. And the guarantee is that functionally, any one of these implementations will work, will do the computation correctly, will interact correctly with the rest of the system. Of course, some implementation may be better than other because they are Pareto optimal in a bi-objective space of performance and cost, latency area. Some may be compared into this Pareto curve, and you want to decide, depending on a lot of consideration that are maybe system level consideration, whether you want to dedicate more area to go a little faster, or you don't want to dedicate more area, go a little faster. But this is part of the design space exploration at the level of the component. And you know that if you specify your components such that you can instance automatically many different implementation, you increase the reusability of your components across many different systems. And this is what this decoupling of the local computation from the communication, from the design of the system guarantees for you. And this is how, to a certain extent, the notion of socket is the, if you will, inherits from the ideas of latency design of the shell. At the time, the variations in latency was on the channels connecting the components. Now you have that because the network on chip, of course, is per se a best effort type of system, communication system. But here you have also the variation of the latency in the local computation. And you are guaranteed to have a functionally correct system. So hopefully this explains why this is important in the context of open source hardware and reusability.
Now, just a quick question.
Yeah, let's go back, please.
So when you say about the local latency sensitive, So does it mean that if, for example, if I have a floating point unit there, each one of the blocks, is that the packets that it can come and in and out can be, the relative order can change? So because if you change the relative order, so one thing is to have latency sensitive,
no, in general,
delay the packets, but the order of the packets can have other impact on the functionality of the design. So do you allow to change the order of the packets or not?
No, in general, you don't. In latency sensitive design, one of the key principles is that on the channel, the order is preserved. Now,
and if there are two channels, what happens?
Depends
or the shell has only one channel.
Okay, so depends on which level of granularity we talk. In general, if you're talking about classic latency sensitive design, or if you're talking about an accelerator in the context of ESP. In general, if for classic latency sensitive design, if the shell has a single channel, there is no problem of ordering because the input will, the channel is ordered, because a channel in latency sensitive design is a lossless queue. You can see it as a lossless queue. So the order is preserved. If you have multiple input channel and multiple output channel, the shell makes sure that the computation progresses when you have the corresponding tokens according to the order of the computation. So this is in latency sensitive design. When we talk about an accelerator in this context, inside a system, if we talk it at the macro level, what it means is that you have that the computation of the accelerator progresses, of course, progresses as function of the particular implementation that you decided. You can take an implementation of the accelerator which has slower, higher latency, maybe has less parallelism, or could be faster, lower latency, but then you have created, I don't know, you have unrolled the loops more, you have created more functional units, you have a bigger private local memory with more banks and so forth. But this computation happens inside the accelerator tile, which interacts with the rest of the system based on the NOC. The NOC, of course, has its own protocol and supports at any given time multiple communication. But the NOC provides the stream of data in and out the accelerator according to the order at which the accelerator asks them. And that is preserved. It's preserved by the NOC, and it is preserved by the local computation. So,
okay.
Please.
The NOC cannot reorder packets. Either.
No, the NOC typically not reorder packet of one transaction, let's say, because maybe this wasn't immediately clear, but or maybe it is. This accelerator, as I said, they do coarse grain tasks. So, for instance, you have that they operate on megabytes of data, which are stored in main memory. They are invoked by software and say, I don't know, compute the FFT on this huge matrix. And this happens through multiple iterations between the accelerator and main memory with multiple load, compute, and store. And there is no reordering of that. The NOC just returns the data in the order that the accelerator asks.
Sorry. Okay, so if there are two, the accelerator triggers two loads, the loads have to come on the same order.
But two different accelerators, you're saying, two different accelerators.
No, the same accelerator. The same accelerator triggers two loads.
The same accelerator triggers two loads. Ultimately, this send a request addresses to memory in an order and return with according to that order.
Okay.
One, I guess, could change that, but this is adding an additional layer of reordering, but this is not typically what we do.
Okay. Oh, yeah, was understood.
Okay, good. So then let me see. I think we are running a little bit late. So this is best to tell you that there is a graphical user interface that should be intuitive. You can configure the ESP matrices in terms of the number of tiles, the type of tiles. You can decide depending on which capabilities you have in terms of accelerator. Here you see we have a mix of the accelerator designed by us, third-party accelerators, and we have different processors. You can add monitors for FPGA that are very helpful when you do research to monitor transaction, to monitor activity on the network. You can decide the configuration of the caches. You can decide how many memory tiles and IO tiles you have. And when you're ready, you generate the SoC, and you get really through push button for the supported FPGA, the bit stream that you can use. So let me just quickly show you very quickly a few examples how we use this in our research. Before I mentioned this wide area motion imagery application of which has multiple accelerators. This you see, this is a paper that we published now 4 or 5 years ago, but it's still a paper where it shows a lot of the capability of ESP already at the time when it wasn't open source. So in this case, you have a 4x4 matrix. You see at the top, you have 12 accelerators. You have 1 processor and 1 I/O and 2 memory tiles. In fact, through the configuration, you could go from 1 memory tile to 2 memory tiles, and this is what we did here. And what you see here live, the computation with the particular the NOC traffic, and also you see the estimation of the power, because one thing we were doing for this particular research, we were focusing on also dynamic voltage frequency scaling for a future chip, and this FPGA supports frequency scaling because it has multiple PLLs, and we could associate a PLL phase-lock loop for each tile, but it doesn't have, FPGA typically don't have multiple integrated voltage regulators. So the power consumption is estimated, but the frequency changes. And so what we could do here, we could change independently the frequency of each accelerator. And so depending on the, and we develop, which is described in that paper, control algorithms that depending on the congestion on the network and whether the accelerator is able to receive data and emit data on the network at the right speed, we were either raising the frequency at which the accelerator was operating or lowering the frequency. And so this we could do it automatically so that we avoided running at a high frequency if the network was congested for that particular accelerator. And so, of course, these 12 accelerators all are connected, are part of a computation. They work some sort of a data flow that I showed you before. And so the interesting thing is that by adding this capability and by playing with how many memory tiles we have, we could reach through some sort of design exploration at the system level, we could reach a configuration where the network was not too congested and where each accelerator ran dynamically at the right frequency or a good frequency, let's say a proper frequency at any given time. And overall, the latency of the overall computation was better, was reduced. And so if you're interested, I invite you to take a look at the paper, and these capabilities are available in ESP since we made it available in public domain. This is more recent research where we, which is an example of research that we have done, more or less say architecture, computer architecture type of research, and using ESP. So here we show how, first of all, it makes sense to have different coherency models for accelerators. For a while, we ourselves focus on non-coherent DMA, non-coherent direct memory access, because it makes sense for a lot of coarse-grained accelerator exchanging huge amount of data with main memory. But then we started noticing that, okay, we started thinking maybe it makes sense to leverage the last level cache to reduce the number of transactions with external DRAM. And so you can have last level cache coherent accelerator. In fact, this can come in different flavors. And then you can also have fully coherent, in which you know, in some cases, depending on various conditions, may also be an interesting proposition. And what we show is that you can implement all these with relatively small overhead inside the socket of the accelerator in a way that is completely independent from the design of the accelerator. And so if you're interested in this, there is this paper, this IEEE micro paper gives you more insight and also a pointer to a NOx paper, which explains how we implemented this coherency on a distributed way on the NOC, such that it can scale as we scale the number of memory tiles and last level cache from 1 to 4. Could scale to 1 to n, but our FPGA arrived up to 4 memory controllers. And this is in fact what it shows here from that paper, the figure how we can just configure and play with different examples, add, change the number and mix of tiles, or for the same number of accelerators, change the number of memory and automatically generate the partitioning of the last level cache and the addition and the interface with the memory controllers. And then this is an example more on the methodology side, if you will, of research, more CAD. So this was a paper that we published last year at DATE. In fact, my student Davide got actually candidate best paper for this one. And this is the paper where we explain how we leverage ESP and another open source project, the one I mentioned before, HLS for ML, which is very interesting. And I invite you to take a look at this project. I think it is one of the, in my opinion, most interesting projects on the generation of accelerators for embedded machine learning, and it continues to progress. So we leverage that, we combine it with ESP, and so this is an example where we created this first application-specific design flow, and we created some sort of a paradigmatic case study, an application where we have some vision kernels, and then we use a machine learning kernel to do some sort of object detection. And so certain things can happen in hardware, certain things in software. And as we developed this, although the goal was mostly developing the design flow, we also made some additional contribution to ESP. Like in particular, we created the point-to-point accelerator-to-accelerator communication that now is available in public domain. And another example is when we studied the NVDLA, and this is another example of how we show how you can integrate third-party accelerator. And from the viewpoint of a methodology, here we show that you can quickly configure different SoC with multiple instances of the NVDLA. You see a 2x2 with one NVDLA, a 3x2 with two NVDLAs. Then I don't show the one with 3 NVDLA. I show the one a 4x4 with 4 NVDLA. And also, you may notice that we scale up the number of blue tiles, which are the interface to external memory. And by combining the scale up of the NVDLA accelerator with the interface to external memory, we are able to have some linear speed up in terms of the frame per seconds normalized that we can compute. And so this is something that we presented at CAR5 last year, and we are currently writing an extended version of this paper. And then a few words. At Columbia, I've been wrapping up. I've been teaching system on chip platform now for 10 years, which is now is a course in the upper level curriculum. It started initially as a PhD course, a seminar, and then it evolved. Is a course that where we really focus on mastering the hardware software aspect of integrating heterogeneous components, but to a large extent means accelerators, into a complete SoC. So we leverage our experience with ESP. We teach the design of these components in order to make them reusable. And so we teach a design with system C and high-level synthesis, so that the goal for the students is not to design one implementation, but to design a specification from which you can obtain many different implementations. And each of them, developed by the students, we can plug it into the system, and they work regardless of whether they need more or less clock cycles to do the computation, because of course the interfaces are latency sensitive. And so we focus a lot on this idea of using Pareto optimality as a matrix for design reusability. If you think about it, the more implementation you can generate on a Pareto curve, which gives you the trade-off between cost, area, power, and performance, so the denser and bigger is the Pareto curve, the more usable is your component, because you can use it the very low power and low cost, maybe low performance for certain type of application where you don't need that for certain type of SoC. And instead, if you do a high performance SoC, maybe you're willing to put more area and more power and get a higher performance from that particular accelerator. And so that's the concept of multi-objective optimization space driven by Pareto curves. And there is a paper where, which I wrote a couple of years ago, explaining how we organize this course. There it has a theory part and a practice part, which I already mentioned, so this I'll skip it. And of course, we are also doing this now. So we started developing on the ESP website a page where we describe some of the projects that we have assigned in our courses at Columbia around the design integration of accelerator, some of the steps and how we use the accelerator flows. And this leverages other resources on the web page, in particular the fact that we have quite a bit of hands-on tutorials that teach you certain key parts of ESP. For instance, there is an hands-on tutorial on designing an accelerator with system C and high-level synthesis. Another one on designing an accelerator with C and high-level synthesis. Another one on combining accelerator into an SoC. And so it allows you a gradual exposure to different concepts inside ESP. And then we have also, every now and then we give tutorials which are more comprehensive. And so these I'm just doing a little bit of publicity. If you want to know more about ESP, we are going to give a tutorial at ISPAS in the end of March, and then one at ASPLOS in April. And there will be some commonalities between the two tutorials, but also differences. And then that's it. So thank you. And thank you for your patience. I think it was a little bit more than 1 hour. So in summary, ESP is this open source SoC platform, which really is meant to promote the open source hardware community and movement. Is our contribution to the open source hardware community. Our goal is to support the realization of more scalable architecture for SoC that integrate more heterogeneous components, and thanks to a methodology which is more flexible in the sense that it accommodates different specification languages and different design flows. So, as I said, was conceived as a heterogeneous integration platform from the start, and we have been testing it through teaching and research at Columbia. And so really we invite you to use it and also to contribute in the spirit of open source hardware community. And I think a few more links. There are also videos on the webpage, so I invite you to check it out. Thank you for your attention. Let me know if you have other questions.
So the virtual clap.
Great talk.
Thanks. Thank you for your patience.
No, it's a very good talk. We really work on this topic area. So let's see if there is any question from the students. Being on a webinar is a little bit harder.
Of course. Maybe I hope that I will be able to give you an update in some future when we can meet in person, and I'll visit Santa Cruz, which has been a while. Any question from the students?
So one thing that it's a little bit related to that, why I was asking, because one of the focus that we're trying to do is have fast compilation. And what you are saying is that now what you are trying to do is to do the tiles so that you don't have to recompile everything. So do you have an, even though the tool is not out, how well it's working, or what are the challenges there that you're having?
And of course, well, one challenge is that we have to build on top of commercial tools, of course. And so we, as you may know, these FPGAs offer you certain capabilities in terms of dynamic reconfigurability and partial reconfigurability, what I mean, more than dynamic. Also dynamic, because you can also partially reconfigure while the FPGA continues to operate. And so the challenges are that, of course, you have to build a bridge between the capabilities offered by these tools and the goals of a project like ours. And so hopefully, and seems promising, but you know, we are in the middle of the research. So I expect progress this year. And hopefully by the summer, maybe we will be able in a position to have a result where we can submit a paper on this. But what is that we are trying to leverage? Maybe it's obvious, but we are trying to leverage the modularity of ESP. Now we have different tiles, and you could imagine that in a system where you have a few processor, a few memory tiles, a few IO tiles, and a few accelerator tiles, maybe what you want to change is just the accelerator, while one or two accelerators, while keeping everything else the same. You may want to do this at design time because, for instance, you are focusing on optimizing one accelerator. You have already optimized it locally, and now you want to see it in action in the whole system, but you don't want to recompile always everything. Or you can focus this, you can apply this at runtime. For example, if you are constrained and you need to swap accelerators. So that we are looking at that. I shouldn't say much more because it is a research done in collaboration. I think we are close to make a nice contribution. The challenges are exactly to make it in such a way that we can leverage a lot of what we have already in ESP and add it as a new flow. And then people can use it. And
you are looking at partial reconfiguration, not the macros, the blocks. In the silence, you have the concept of a block. The problem is that when I tried a long time ago. But when I tried long time ago, the problem is that I was able to do a macro and then move it, but it was very sensitive. And most of the time it had to reroute again. So even though I have done it was a tile kind of design, and I can cut and paste the same thing, but it was very, all the stars have to align perfectly. Otherwise the tool was triggering a replace and reroute again, which was breaking all the the synthesis was not retriggering again, but all the saving time for doing blocks or tiles was not there. Now you are doing the partial reconfiguration path is a different path, so I didn't try that one. So I don't know.
Yeah, so because I guess we are leveraging, first of all, this is an academic effort. And so right now the idea is to see if we can leverage the modularity that we have. And so, but this is good feedback that you're saying. So I always share it with my students who are working on this. The idea is that I think we really want to, ultimately, we want to enable more an easier use of FPGA for prototyping, because we think, and I'm not the only one thinking this, but we think that for a lot of research in SoC design, SoC architecture, sometimes computer architecture, you can really leverage FPGAs to do some interesting experiments that which with simulation are tricky or maybe not feasible. And so this would be the next step also for us. And so the goal is, like all the other things, is to share it. And so right now, since we put ESP in public domain, most of the time, and by the time we publish the paper, we also share the contribution, and so people can use it and improve it and build on top of it.
Okay, thank you. Is there any other question?
I'll go while the students think of some. This is a great talk. It seems like it's be really helpful for me to take an accelerator, put in a tile, and put an SoC. What if I want to perhaps change the structure of SoC a little more? Like if I want to maybe change the NOC topology, maybe I want to make a very high bandwidth link between memory and a certain accelerator title. Is that easy to do?
Yes and no, meaning it's not as easy as the things that that I show you, the things when at some point I had the accelerator flow and design flow. If you do things that we do routinely for this type of accelerators, like this type of streaming accelerator with do pipeline in parallelism, and they interact with main memory, and they interact to point-to-point communication, that we have it. But if you are saying, I want to change, for instance, the services such that the accelerator has a dedicated path to memory, that may and create a NOC for that. That is doable, but it may require for you to develop something on top of ESP, depending on what you want to do. So just the extreme case, let's say you want to change the NOC design. That is something that, for various reasons, if you want to even change the topology, let's say, that is a bigger effort than changing the configuration of the NOC based on the topology that we provide, of course. In that sense, I think everything potentially is doable. Certain things require bigger effort. We have introduced point-to-point communication. So point-to-point communication allows an accelerator to interact with another one, and through a pull mechanism, the accelerator downlink. I didn't explain this today because it is, but it's explained in the date paper. Through a pull mechanism, the downlink accelerator gets data from the uplink accelerator, and there is a capability to configure this relationship, which is directional relationship, in software when you configure the accelerator. I guess you could consider building on top of that the kind of communication that you would like, dedicated with memory. Right now, we don't use it to point with memory. We do point-to-point between accelerator. Make sense?
Yes, definitely.
So,
great.
In other words, I hope that I'm not discouraging. In fact, I encourage not only the use of ESP with the capabilities that we offer, but also research in architecture or in methodology with design flows that would contribute to ESP. So like, for instance, a better NOC, or like a new service implemented in the socket. This is for the architecture. For the methodology, a new flow for a different application domain specific. That I would love it. Like we have this one with HLS for ML. We are thinking about another one now. But these are all contributions that would be main contribution, in the sense, important contribution to either the architecture and the methodology. And then, of course, there is the contribution of just open source component like processor and accelerators. And we pay attention to components that are shared in open source, And we continuously evaluate. Let's see how easy it is to allow the integration with these components. So this is what happened, for instance, with this EBEX processor for IoT type of applications. And so there is also opportunity for contributing collaboration, and we are very interested to help and to have a conversation on this if there is an interest.
Great. On the methodology front, is there any support for helping with verification? Obviously, I write verification for my own components, but help with the integration and that sort of thing. Is there any support?
And it can be improved. Let me put it this way. We have certain capabilities in terms of, I went fast on that. When you integrate the component, or now you can evaluate, but the evaluation is, in terms of validation, is a lot of simulation and then a very quick path to prototyping, and so to evaluate the components on a complex scenario on the FPGA. There is more that can be done, for instance, in terms of formal verification. So I think there's a lot more.
Always more you can do for verification, right?
No, but what I'm saying is, there's always more, right? You are completely right. What I'm saying is that to the extent that one accepts that some of the compromises, or some, maybe more than compromises, they are compromising, but some of the decisions that we have made, like for instance, this tile architecture, this decoupling of the computation from the communication, this idea that you have accelerator tiles, memory tile, processor tiles. Once you do this, to the extent that you consider this acceptable for your purposes at the system level, at the SoC level, then one can use this to break down the complexity of verification. No? And so then you say, okay, I validate a component, making certain assumption on the system or on the NOC, or I validate the NOC, making certain assumption on the components. And that, there is a lot, I think, that could be done that, we have limited resources. And so in terms of formal verification, that would be fantastic. Makes sense, no?
Yes, thank you for that answer.
Okay.